Lesson 6.5 is going to focus on geometric sequences. So now we know what a sequence is. We know that it is an ordered or a set of ordered numbers. Just a quick review. So a set of ordered numbers. Okay. And typically there's a pattern that once you establish, you can use it to predict. We talked about arithmetic sequences already, and arithmetic means we are constantly adding or subtracting the same quantity. And now we're going to focus on geometric sequences. In a geometric sequence, the ratio, okay, so it's the ratio that's constant, meaning that we're going to be either multiplying or dividing by the same quantity every time. We look at it in terms of multiplication. So in a geometric sequence, the ratio between each pair of consecutive terms is always the same. This ratio is what we call the common ratio, and that's going to be the pattern that we're going to be looking for. So on arithmetic sequences, we were talking about the common difference. Now we're talking about the common ratio. So each term is found by simply multiplying the previous term by this common ratio, and that will always give you the next value. So how is this a little bit different? Well, before we were if we wanted to establish something was arithmetic, we either added or subtracted, and to find out what they were adding or subtracted, we would subtract the new minus previous. Here we're going to take the common ratio, which means if we were to divide this new value divided by the previous one, right here, 5 divided by 1, we should get the same answer as if we do, for example, 25 divided by 5. Well, that's still equal to 5. Or if we do 125 divided by 25, every time we divide a new by previous, divide new by previous, we get the same answer, which is a 5. All of these equal 5. So A, that means that this is a geometric sequence because that common ratio is consistent and it's the same all the way down the line. And B, that value that we got, that 5, that is your common ratio. And once we establish that one, then we can multiply the 125 times 5 if we wanted to get the next number in the sequence and so forth. Okay, so just like last time, it's fine to come up with a ratio and use it to extend the pattern if you just need the next few terms. But we also have an equation that helps us find any term in the sequence. Even if it's, the 4019th term, we would certainly not want to expand it that many times. We could use our formula for that. And I'll just make a note here. If this is feeling like this multiplicative pattern feels familiar, you would be right, because we saw this a lot when we did exponentials. So just like those arithmetic sequences are a different perspective on linears, these geometric sequences are a different perspective on the exponential patterns that we were exploring when we did exponential growth, exponential decay, that sort of thing. And as such, you're going to notice hopefully you're going to find this formula familiar. You see the exponent or the power here. You've got the first term and the common ratio. And as long as you have those two ingredients, as long as you know what is the common ratio, because we're going to put that as our base, and what is the first term in the sequence, then you can just drop those in here and here, and you have your equation. This one does not require any simplifying either, which is kind of nice. Okay, so just a few things there. Let's go ahead and practice both identifying whether it's geometric compared to arithmetic or maybe something else, and also how to generate the equations and so forth. So we'll do several of these. So let's start with number 1. So we have a sequence here, obviously, like I said, an ordered list of numbers. We want to know if it is arithmetic, geometric, or neither. We can certainly start to try, if we want to test for arithmetic first, we can do that since we're a little more familiar with that. All we would have to do is take this new value minus the previous and see if we get the same common difference every time. So if I do -4 minus 1, I get -5. Let's try it here. If I do 16 minus that -4, I do not get the same number. So this does not have a common difference. I can already see that. We can also already just kind of see that this is not going up by a constant amount. It starts off with a small difference and then it gets real big. So we can rule out an arithmetic. So now let's try it for geometric, which is what these guys are all about. So if we were geometric, then if we divide this new -4 by the previous number, we get this answer. Let's find out if we get the same all the way across. Then we'll try it with a 16 divided by the -4. Look there, it's the same number. I'm going to try the last one just for good measure. If I do -64 and I divide that by that 16, which is the number right before it, I get the same exact ratio every time. This is your common ratio. And first of all, it tells us that it's geometric, and it also tells us what they are repetitively multiplying by should we want to extend this pattern. Okay, so based on this, we can determine here, this is geometric. And to explain our reasoning, we're going to say this has a common ratio of -4. And that's how we know, okay? We can say it has a common ratio. Okay, all right, let's try number 2. So if we check out number 2, again, we can start with the arithmetic test, see if we look out there. So if we do 7 minus 3, again, if we're testing for arithmetic, we're going to find the common difference and see if it's, well, we're going to find the difference and see if it's a common difference. So we're going to find the difference and see if it's always the same. So we've got 7 minus 3, that gives us 4. What if we do this next pair, 11 minus 7, also 4. And then this last one, 15 minus the 11 is also 4. So this did have a common difference, like the arithmetic sequences we did yesterday. So this one's arithmetic. And if we tried the ratios, by the way, we would see it would fail. So since we're on geometrics, let's do that. So if we did 7 divided by 3, and we compared that to the next fraction, which would be 11 divided by 7, we would start right away to see, oh yeah, those are not the same ratio. So this does not have a common ratio, but it does have a common difference, and that's what makes it arithmetic. Okay, so we're going to say it does have a common difference of 4, and it has a common difference. Okay, where this one had a common ratio. Okay. All right, let's try number 3. And we've got 2, 4, 8, 32. Let's start with a common difference since we're already on that. So let's see, 4 minus 2, that's our first difference. And then here, 8 minus 4, that's not a match. And even if we try the next one, 32 minus 8, we can rule out an arithmetic here because the difference is not a common difference. The difference is changing, and if it's not exactly the same all the way down, then it's not an arithmetic sequence. So that's out. Okay, let's then check for geometric by finding the ratios. Maybe we'll look out here. So let's see, 4 divided by 2 now. So that's the first ratio. And then 8 divided by 4. 8 divided by 4, also 2. Let me check the next one. 32 divided by 8. Oh, this is interesting. So we got a ratio that was the same for the first two, but it didn't work for the next one. That's why it's really important to check all of the values you have visible to you. So 4 divided by 2 is 2. 8 divided by 4 is 2, but 32 divided by 8 is not 2 anymore. So the ratio did change. Eventually it did. And this means that it is not geometric either. So it ruled out arithmetic, and now we can rule out geometric. So we're just going to say this is neither one. Okay. Go ahead and stop here and try number 4 and see if you can determine which of the sequences this is or if it's a neither. Okay. So hopefully you got neither here, and you would be correct. This, when we tested out the common ratio, it failed pretty quickly here. When we do 9 divided by 12, we get a very different answer than when we do 7 divided by 9. So definitely not geometric. And then when we looked for a common difference, 9 minus 12 is not the same as 7 minus 9 either, or 5 minus 7 for that matter. Sorry. So those are not the same. every time. So this is neither. This first one was different than the other two. Okay, so hopefully this is enough practice and you know how to determine if it's geometric, arithmetic, or neither one. We're going to finish out with number 5. Try number 5. Let's see how that goes, and then we'll move on. Okay, so on number 5, if you determined that this was geometric, then we're in great shape. This did have a common ratio, that's an R value, of 3. So 6 times 3 is 18, 18 times 3 is 54, 54 times 3, and so on. So it has a common ratio. Okay, all right. Flip it over. Let's go to the next section here. On these, it says write the next 3 terms in the geometric sequence. So we don't have to determine any longer whether or not it is. We just need to extend the pattern. We are being told or given that it is geometric. So we don't necessarily have to test each value. All we really need to find out is what is the common ratio, what is that R value, and then use it to expand the pattern. So you may already be able to tell that 7 times 3 is 21, but if you're not sure, like I said, you can just divide the new divided by the previous. That'll reveal to you what the R value is. And you shouldn't have to check every one because they've already told us that it's geometric, but if you want to just, play it super safe, you can do that. And you'll see that you get that 3 for every single one of these. So you have an R value, or a common ratio of 3. So now let's actually apply that. So what that means is that they're multiplying by 3 each time to get the next value. Once we have been able to determine that, then to expand or write the next 3, we just start with this last term they gave us and multiply it by our R value, and it'll give us what comes next. So after 189 would be 567. That would be the 4th, or I guess the 5th term now. And then that times another 3, we just continue the pattern, would be 1,701, and that times another 3 would be 5,103. So these would be the next 3 values in this particular geometric sequence. So 1,701, and then 5,103. There you go. Okay, those will be the next 3. Let's try number 8. So on number 8, we look here. Again, they've already told us it's geometric, so we just need to discover what is that value of R. So we'll take a mu, and I could do that for any of these. So maybe the 144 divided by the 288. As long as they're right next to each other, then I'm good to go. Okay, so it looks like it is 1/2 or 0.5, however you want to write that. And so we're always multiplying by 1/2 to get the next value. Once I know that, then I can go ahead and just extend this. They left off at 72. So I'm going to start with 72 and multiply it by that 1/2. And that tells me that the next value is 36. And then if we multiply that by another 1/2, the next one would be 18. And then times another 1/2, the next one would be 9. Those would be the next 3 values after 72. It would go to 36, 18, 9 if I just extended that pattern. Okay, let's check this one out. I don't know if you've noticed, this is the second one I think we see like this, but one of the cool things about geometrics that kind of gives it away that it might be a geometric is the fact that it can involve those negatives and they end up flip-flopping. So you can kind of see a positive, a negative, a positive, a negative. That's a good indicator that you might have a geometric on your hands. Arithmetics won't do that. Flipping back and forth. But let's go ahead and still just do what we do. Let's find our common ratio here. And then we will use it to extend the pattern. And if I left off at -40, well, actually, let's find our R value, sorry. -10 divided by the previous. So that means that we multiplied by a -2 to get -10. -10 times 2. -2 is 20. 20 times -2 is 40. So yeah, definitely a -2 as our common ratio. And then we can pick up where they left off. They left off at -40. So if we multiply that by -2, that means our next number would be 80. Times another -2 would be -160. And times another -2 would be a positive 320. Those would be the next 3 terms in that sequence. Okay, All right, let's quickly talk about graphing here. When we're talking about graphing, it's going to be quite similar to what we did with arithmetics. We're going to graph this sort of relative or compared to its position in the sequence. So I'm going to sort of generate a, let's see, like a little mini table, if you will. Write the next 3 terms in the geometric sequence and then graph it. So yeah, we'll talk about that in just a moment. Okay, so we're comparing to the position and then what the actual term is. So 12 is the first term in the sequence, 6 is the second, the third term is 3, the fourth term is 3/4. We're now going to expand the 5th, 6th, and 7th terms, and then we'll graph that. So let's take a look. It looks like they are multiplying by 1/2, but again, feel free to check that if you're not sure. You can take any new value divided by the previous, and sure enough, our R value here is going to be 1/2, 0.5 or 1/2, okay? And so if we left off with 3/2 here, oops, sorry. Okay. If we left off with 3/2, and then we multiply that by 0.5, we get 0.075. You can do that as a fraction. In fact, let's do that. Let me be consistent here. We're going to do 3/2 and multiply it by, and I'm going to do that 0.5 as a half. That way, they started with a fraction, I should continue with a fraction. So that means that the 5th term is going to be 3/4. Okay. And then if we take that guy and multiply it by another 1/2, the next one would be 3/8. And if I multiply that by one more time, another half, then we're looking at 3/16. Okay. And then we plot those on the graph. Okay. And we're going to use the x-axis as the number of terms in the sequence. So 0, 1, 2, 3, 4, 5, 6. We've got about 7. I'll label all the way down, but we're going to only really have about 7 values here. And then we will graph the actual terms here on this side. And I think I'm going to be okay. The 12 might be falling off a little bit off the grid, but not too bad. So I'm going to go by ones here as well. Feel free to adjust your axes when you need to, when multiple problems sort of jump out, or fall off, if you will. And then we know that the first term in the sequence was at 12, so this goes to 10, so 11. 12 is probably about right there. The second term in the sequence was 6. The third term in the sequence was a 3. The fourth term in the sequence was 3/2, which is 1.5, so about right there. Okay. The next one was 3/4. This one was the 5th term, so that's about right there. And then 3/8, which is a little less than half, and 3/16, which is about a quarter of the way. Okay. So there are our values. And again, we had already talked about this, but if this kind of feels familiar, this one-sided curve that's just going to keep getting smaller and smaller, but never quite reach 0, you're absolutely right. This is exactly what the exponentials do, okay? All right, so that's a graphing example there. Let's go on to actually using the formula that we had on the other page. So we're going to write an equation for the nth term here, and then use it to find the 6th term in the sequence. So just a quick reminder, I'm going to write this over here. This is our formula for the nth term of a geometric. It looks like this. Okay, and again, as long as I have the first term and the common ratio, that's the only ingredients I need. So if we're going to do this for number 13, let's take a look. We know that the first term in the sequence is 561. And then the other ingredient that I need is a common ratio. So again, I'm going to reach for my calculator here. Determine what the common ratio is by dividing a new term divided by the previous and seeing what that gives me. Okay, and that's 0.3 repeating, which is the same thing as a third. And I can test this with the other ones like 243, divided by the 729. I'm still going to get that. So that's the same thing as a third. Because I don't love decimals and definitely not repeating ones, I'm going to do like that because it's more accurate. Excuse me, and easier to work with. All right, so all I have to do is go to gently put these guys in where they belong, and I'll have my equation. And the good news here is, again, these don't even need to be simplified. They're already simplified as they come. So I'm starting with 6,561, and then my common ratio is going to be a third, and I'm raising that to the n minus 1 power. And that, my friends, is your nth term equation. That's sort of the first part that they wanted us to do here in the directions, was to write an equation for the nth term. And then, once we have it, we can use it to find the sixth term. So now if we want the sixth term in this sequence, all we have to do is plug that in for n, show that here in our work. Okay, it would look like that. If we simplify that, we're looking at 1/3 to the 5th power. It's always one less. And then let the calculator do the work for that. So we'll do 6,561. The 1/3 is our common ratio. That becomes the base. And we're raising this to the 5th power. And the answer is 27. So that would be the 27th. 27 would be the sixth term in this sequence. There it is. Okay. All right, try this next one. Try number 14. See what you get there. Okay, so hopefully you are determined that the first term in the sequence was 8, and the common ratio here was -3. If you divide each one of those. When you put that into the nth term equation, we start with 8. This is our common ratio. That becomes the base of our power here. And this is our first part of this problem, which was writing the nth term equation. Okay. Once we have that, then we can solve for the sixth term by just plugging in that 6. So if we want the sixth term of the sequence, it's going to be 8, -3 to the 6 minus 1 power. And hopefully you guys got -1,944. If that's what you got, then you are in great shape. Okay. Let's do number 17. Let's do one more. We'll do 17 here. And that's off of a table, but that really doesn't make a difference. That's just a different way of organizing the same sequence. So what they're doing here is very similar to what I did up here to make a table so we could graph it. It's the same idea though. N is the position of the value, and this is the x. So the first term in the sequence is 11. The second term in the sequence is 44. The third term in the sequence is 176, and so on. So let's do this guy right here. If we're going to write the nth equation, right, all we need is the first term, which in this case is 11, and the common ratio, which in this case is 4. Like I already know 44 divided by 11 is 4. I can test it with any other one just to make sure I didn't make a silly mistake, 176, but I'm still going to see here that the common ratio for any of these is a 4. That's our R value. So there's our first term, there's our common difference, and -1. Those are the only ingredients I needed to come up with our nth term equation. And then if we want the sixth term now, then we just plug that in there and evaluate that. Let's see what we get here for that. We do 11. 4 is our base. We're raising this to the 6 minus 1, or if you already know that's 5, that's fine too. You should indeed get 11,264. That is our sixth term in that sequence. Okay, so that's how you use a formula. I feel like this one's almost a little easier because it doesn't require the simplification. Okay, let's try one more here just to have a graph example. Let's do number 20. So on a graph, sometimes the points are kind of hard to find. So I would really recommend you pay close attention to your X so you can make sure that you have these in the right order. So really it's like 1, 8. So that means 8 is the first term. Then the second term is like over here. So be careful with these guys being distractions. The second term in the sequence is -4. The third term in the sequence is a +2. The fourth term in the sequence is -1, and the fifth term is at 0.5. Excuse me. So now that I have them a little visually easier to read, then we can go ahead and write our equation. Our first term is 8. Our common ratio, it appears to be -1/2. I can kind of see that -1/2 is -1/2 here, or -0.5. They are using decimals, so maybe we'll use that when we write our nth term. So we would start with 8. This would be -1/2 or -0.5 and -1. This would be our equation with that first term in common ratio. And then again, if you wanted to find the sixth term, you would just put a 6 up here and find out what that is. So let's do that. 8. We've got that common ratio of -1/2. We're going to raise that to the 6 minus 1, or the fifth power. And I get -0.25, or -1/4. All right, I think that looks really good. So we're going to do one of these word problems. We'll finish off with that. We'll do the other one together. Let's take a look at this digital city map. There is one thing you want to be on the lookout for these, so please pay close attention. We're almost done. So a digital city map displays an area of 144 square units. So that's the initial. After you zoom in once, so think about that. This is like one zoom, then you have an area of 272. After you zoom in a second time, you have an area of 136, and so on. And we want to know what is the area after you zoom in 5 times. So you want to be careful here, because don't be tempted. You might be tempted to make this your a sub 1, but this is actually with 0 zooms, no zoom at all. So if you think of this in terms of a table, right, or something like this, this is with 0 zooms is when we are at 544. And then 1 zoom is 272. And then 2 zooms is 136. So you want to be consistent with the language and what they're saying. That means that with 1 zoom, this is the number we want when we are thinking about our a sub 1. So if we have our formula, right, even though this is sort of the initial quantity when it's 0, our formula doesn't use the 0th term. It uses the first term in the sequence, okay? And so, or the one in position 1, which in this case is 1 zoom. So we want to just be careful with that. So it's going to look like this. Now let's find out what our common ratio is. So our a sub 1 is 272. Let's find out what our r value is. So if we divide these guys, I believe that's going to be a half, but we're about to find out. 272 divided by 544. Yep, 1/2. Okay, so this would be our formula for the nth term. So when it says write an equation for the nth term, this is what we would want in that spot. You could use a decimal or a fraction, but that's our equation. And then we can accurately decide, okay, well then after 5 times, then that means n is 5. So after 5 times, now we just plug that in here. 5 minus 1. Let's find out what that is. If we start with 272 on the first zoom, we're doing 1/2 every time. We raise that to the 5 minus 1, which is just a power of 4. We would be at 17 square units. There you go. Units squared. Okay, and that is our lesson over geometrics. We'll do the next one in class.